Operating a dual voltage motor designed for 230 volts on a 120 volt power source can indeed cause damage. When the motor is connected to 120 volts instead of 230 volts, it receives a lower voltage and consequently draws more current to attempt to produce the required power. This increased current flow can lead to several problems within the motor, primarily overheating of the motor windings and potential damage to the bearings, ultimately resulting in premature wear or even complete failure. While operating the motor on 120 volts for a short duration, such as less than 30 seconds, might seem inconsequential, it can still inflict damage if the current draw was significantly elevated during that period. Even if the damage isn't immediately apparent, it could manifest later in the form of reduced performance, increased noise, or premature failure of the motor. The symptoms you described, such as a grinding sound and the motor's inability to operate at the correct revolutions per minute, specifically 1750 revolutions per minute, strongly indicate that the motor has likely sustained damage from the 120 volt operation. These symptoms are indicative of potential issues within the motor, such as damaged windings or compromised bearings. The grinding sound often suggests bearing damage, while the reduced revolutions per minute could be related to either winding or bearing problems. Depending on the extent of the damage incurred, the motor may or may not be repairable. The determination of repairability hinges on the severity of the damage to the windings and bearings. Here are the potential repair options to consider. Firstly, winding repair. If the motor windings have been overheated and subsequently damaged, they may require rewinding. This process involves replacing the damaged wires within the motor's core with new ones. Winding repair is a complex and time-consuming procedure that requires specialized equipment and expertise. Secondly, bearing replacement. If the bearings within the motor have been damaged due to the increased current draw or overheating, they may need to be replaced. Bearing replacement is generally a less involved repair compared to winding repair, but it still requires the removal and replacement of the motor's bearings. Thirdly, complete motor replacement. In cases where the damage is severe and the cost of repair exceeds the value of the motor, complete motor replacement may be the most viable option. This involves replacing the entire motor with a new one. It is highly recommended to take the motor to a qualified motor repair shop for a thorough diagnosis and assessment of the damage. A skilled technician can evaluate the extent of the damage to the windings and bearings, and then provide the best course of action. This might involve repair, such as rewinding the motor or replacing the bearings, or it might necessitate complete motor replacement. When a dual voltage motor, designed to operate at a higher voltage such as 230 volts, is inadvertently connected to a lower voltage power source like 120 volts, a series of events occur that can lead to motor damage. Understanding these events is crucial for comprehending why such a mistake can be detrimental. Firstly, reduced voltage. The most immediate effect is that the motor receives significantly less voltage than it was designed to handle. This reduced voltage impacts the motor's ability to generate the necessary magnetic fields to operate efficiently. Secondly, increased current draw. Motors are designed to draw a specific amount of current at their rated voltage to produce the required power. When the voltage is reduced, the motor attempts to compensate by drawing more current to maintain the power output. This relationship between voltage, current, and power is fundamental in electrical engineering. Power is proportional to the product of voltage and current. Therefore, if the voltage is reduced, the current must increase to maintain the same power level. Thirdly, overheating of windings. The increased current flow through the motor windings generates more heat due to the resistance of the wires. This heat can exceed the motor's design limits, leading to overheating of the windings. The insulation material surrounding the wires can break down, causing short circuits and further damage. Fourthly, bearing damage. The increased current can also affect the motor's bearings. The higher current can create excessive heat in the bearings, leading to premature wear and potential failure. Additionally, the motor's attempt to compensate for the reduced voltage can place undue stress on the bearings, accelerating their degradation. Fifthly, reduced performance. The motor's ability to produce the required torque and speed is compromised due to the reduced voltage and increased current. The motor may struggle to start, operate at the correct revolutions per minute, or deliver the necessary power for its intended application. Sixthly, grinding sound. The grinding sound you described is often indicative of bearing damage. Damaged bearings can create friction and vibration, resulting in an audible grinding noise. Seventhly, premature failure. The combination of overheating, insulation breakdown, and bearing damage can lead to premature failure of the motor. The motor may eventually stop working altogether, requiring repair or replacement. Considering the impact of running a 230-volt motor on 120 volts for even a short period, it is essential to understand the potential long-term consequences. Firstly, insulation degradation. The insulation material surrounding the motor windings is designed to withstand a certain temperature range. When the motor overheats due to excessive current draw, the insulation can degrade over time, becoming brittle and less effective at preventing short circuits. This degradation can lead to eventual failure of the motor, even if the initial damage seems minimal. Secondly, winding shorts. If the insulation around the windings breaks down, it can lead to short circuits within the motor. These short circuits can cause further overheating, arcing, and potentially irreversible damage to the windings. Thirdly, bearing wear. The increased current and stress on the bearings can accelerate their wear, leading to reduced performance and eventual failure. Worn bearings can create excessive vibration and noise, and they may even seize up, causing the motor to stop working. Fourthly, reduced lifespan. The cumulative effect of these issues is a reduced lifespan for the motor. Even if the motor continues to operate after the initial incident, its performance and reliability may be compromised, leading to earlier replacement than expected. Fifthly, increased energy consumption. A damaged motor may consume more energy than a healthy motor to produce the same amount of power. This increased energy consumption can result in higher electricity bills and reduced energy efficiency. When evaluating repair options for a motor that has been subjected to overvoltage, it is essential to consider all the factors involved. Firstly, diagnosis. A qualified motor repair technician should perform a thorough diagnosis of the motor to assess the extent of the damage. This diagnosis may involve visual inspection, electrical testing, and mechanical measurements. Secondly, winding repair versus replacement. If the windings are damaged, the technician will need to determine whether they can be repaired or if they need to be completely replaced. Winding repair may be possible if the damage is limited to a small area, but replacement is often necessary if the damage is extensive. Thirdly, bearing replacement. If the bearings are damaged, they should be replaced with new ones. It is important to use high-quality bearings that are designed for the specific motor application. Fourthly, cost analysis. The technician should provide a detailed cost estimate for the repair, including the cost of parts and labor. This estimate should be compared to the cost of a new motor to determine the most cost-effective option. Fifthly, downtime. The repair process can take time, and the motor may be out of service during this period. This downtime can be costly, especially if the motor is critical to a production process. The technician should provide an estimate of the repair time and the potential impact on operations. Sixthly, warranty. Any repair work should be covered by a warranty to protect against further issues. The warranty should cover both parts and labor, and it should be valid for a reasonable period. When dealing with dual voltage motors, it is crucial to ensure that the correct voltage is selected before connecting the motor to a power source. Here are some tips to prevent future misconnections. Firstly, labeling. Clearly label the motor with its voltage requirements. This label should be prominently displayed and easily visible. Secondly, wiring diagrams. Provide clear and easy to understand wiring diagrams that show how to connect the motor for different voltage configurations. Thirdly, voltage selection switch. If the motor has a voltage selection switch, make sure it is set to the correct voltage before connecting the motor to the power source. Fourthly, training. Provide training to personnel who are responsible for connecting motors to power sources. This training should cover the importance of verifying the voltage requirements and the proper connection procedures. Fifthly, checklists. Use checklists to ensure that all steps are followed correctly before connecting a motor to a power source. This checklist should include verifying the voltage requirements, setting the voltage selection switch, and inspecting the wiring connections. Sixthly, color coding. Use color-coded wiring to help prevent misconnections. For example, different colors can be used to represent different voltage levels. Here are some additional considerations when dealing with motors and electrical systems. Firstly, electrical safety. Always follow proper electrical safety procedures when working with motors and electrical systems. This includes disconnecting the power source before performing any work, using appropriate personal protective equipment, and following lockout-tagout procedures. Secondly, grounding. Ensure that all motors and electrical equipment are properly grounded to prevent electrical shock hazards. Thirdly, overcurrent protection. Use appropriate overcurrent protection devices, such as fuses and circuit breakers, to protect motors and electrical systems from damage due to overloads and short circuits. Fourthly, regular maintenance. Perform regular maintenance on motors and electrical systems to ensure they are operating properly and safely. This maintenance should include inspecting wiring connections, checking for signs of wear or damage, and lubricating moving parts. Fifthly, professional assistance. If you are not comfortable working with motors and electrical systems, seek professional assistance from a qualified electrician or motor repair technician. Their expertise can help prevent accidents and ensure that the work is done correctly and safely. In the context of the scenario, here is a breakdown of how to proceed. Firstly, immediate action. Disconnect the motor from the power source immediately. Do not attempt to operate the motor further until it has been properly diagnosed and repaired. Secondly, visual inspection. Perform a visual inspection of the motor, looking for signs of damage such as burnt wires, melted insulation, or damaged bearings. Thirdly, documentation. Document all the steps taken and observations made. This documentation will be helpful for the motor repair technician. Fourthly, professional consultation. Contact a qualified motor repair shop and explain the situation. Provide them with all the details about the motor, the voltage misconnection, and the symptoms observed. Fifthly, transportation. Transport the motor to the repair shop for a thorough diagnosis and repair. Ensure that the motor is properly packaged to prevent further damage during transportation. Sixthly, repair assessment. Allow the repair technician to assess the damage and provide a detailed repair estimate. Discuss the repair options and the associated costs before proceeding with any work. Seventhly, preventive measures. Once the motor has been repaired, take steps to prevent similar incidents from occurring in the future. This may involve labeling the motor, providing training, and implementing checklists. In summary, operating a 230-volt motor on 120 volts can cause significant damage due to increased current draw and overheating. Prompt action, proper diagnosis, and appropriate repair measures are essential to minimize the long-term consequences and prevent future incidents. By following these guidelines, you can ensure the safe and reliable operation of your motors and electrical systems.